Hello physical science student, welcome to the next video. In this one we're going to do our last type of radioactive decay, and that's gamma decay. Here's our little picture. There's our parent nucleus, there's our daughter nucleus, and the gamma ray is represented by this little symbol. Sometimes you might see it, or I prefer to draw it like this, a little squiggly thing like that, and that represents a photon. A photon is a little bundle of energy, but it's electromagnetic radiation, hence the waveform. But you can draw it like that or like this. Notice here that they've put these little lines around the parent nucleus. What they're trying to say there is the parent nucleus has too much energy. And usually what happens in gamma decay, that gamma decay is usually after another type of decay, alpha or beta, and the nucleus is then left with too much energy, so the protons and neutrons are readjusting themselves and they just have a little bit too much energy, and that energy is given off as a photon, a bundle of energy. And so the daughter nucleus, all it is, it's the same as the parent nucleus but with less energy, and so the protons and neutrons have arranged themselves in a more stable arrangement. What does that look like? Like this. Okay, there's bismuth 210. That little asterisk there indicates an excess of energy. Could also be a little m, meaning metastable, means it has to decay. And there it is without that symbol, and there's our little bundle of energy in the form of a gamma ray. Notice that none of the numbers change because gamma rays have no mass, therefore they don't change the number of protons or neutrons in the parent or daughter. They are, however, electromagnetic energy, and they travel at the speed of light and have no charge. Now, why do we have excited nucleuses? Exactly why I said. So you can read that if you like. Now, other reasons that nucleuses could be stressed is because of collisions and because of the environment that they're in. We're talking extreme environments here in terms of inside nuclear reactors or suns, or on the edges of black holes, things that are really extreme in terms of physics. They can be excited, and that excitement means that there has to be a release of the stress, and that's where we get a photon. Now, gamma radiation is very penetrating because it has no charge, and it is basically just a little bundle of electromagnetic radiation. So it passes through meters of concrete or lead. Doesn't stop it. So they're going through you right now without doing anything. So they're often used as what's called tracers, and medical tracers, and that's where you would give something that gives off gamma rays to a person. We'll talk about this more when we do in applications, but basically it's so that the radiation can go to some place like into your kidneys or something, and then you can look at the gamma that comes out of your body and the concentration of it, and it actually gets out of your body to the sensor, and so you can actually see things. And so it's quite a common practice, and we'll talk a lot more about medical tracers and their use in medicine. As we said, it's very penetrating, goes straight through a person, but if it is absorbed, it is a big bundle of energy, and so it can have some consequences, and therefore it is still a hazard, both internally and externally. That's it. Not much about gamma. In the next video we're going to learn how to write nuclear equations and how to solve them. We've already seen how they work, so we'll get some hands-on practice with them as well. Cheerio!